Long before the first astronomer traced the path of a wandering light across the vault of the night sky, long before the earliest sailor dared to trust his fragile vessel to the whim of the sea, humanity sensed a rhythm in the world that seemed older than memory itself. On the wind-beaten shores of prehistoric coasts, where tribes carried fire in hollowed stones and painted animals on cave walls still damp from the tide's breath, the sea rose and fell with the precision that no beating drum could match. People who knew nothing of celestial mechanics, who lacked numbers, diagrams, or even the idea that distant bodies pulled at one another, watched the ocean inhale and exhale as though it were a living creature sleeping beneath the earth. They noticed that certain days brought the waters unusually close to their shelters, while on others the distant reef lay exposed like a stone ribcage beneath the sun. And while they feared storms and revered the spirits of mountains and rivers, it was the ceaseless, faithful swelling of the sea that first taught them to mark time not by the rising of the sun, but by a mysterious force that governed the night. In those early ages, the moon was not a lamp in the sky, but a deity whose changing forms stirred prayers whispered in dozens of emerging languages. On Mediterranean cliffs where ancient peoples built their first shrines, fragments of polished seashells have been found arranged in spirals that mirror the lunar phases, suggesting an understanding, or at least a reverence, that the pale wanderer above exerted influence over Earth's waters. Across the world on Pacific islands, navigators who steered their outrigger canoes across open ocean recognized that the tides shifted with the moon's cycle, even if they could not yet articulate the nature of the connection. Their knowledge came from observation, from generations of elders whose memories were as much a map as the lines of stars overhead. To them, the moon was a companion whose silent presence foretold when the lagoon would fill with fish, or when the reefs would reveal pathways for traveling between islands otherwise isolated by miles of rolling blue. As civilizations grew, so too did their fascination with this nightly sentinel. In ancient Sumer, scribes etched records onto clay tablets describing the regular appearance of unusually high tides, correlating them with the moon's position in the sky. Their temples, carefully oriented to celestial alignments, may have served as both places of worship and instruments for tracking the heavens. Farther west, in Egypt, priests along the Nile observed a gentler form of tidal influence, subtle compared to the ocean, but still perceptible in the river's eternal pulse. They believed the moon imbued waters with life-giving power, its phases tied to the fertility of the soil itself, and thus included lunar symbols in the rituals that ensured the continued flooding the kingdom depended upon. On the opposite side of the world, Chinese astronomers compiled meticulous records of celestial behavior, noting that the greatest tides aligned with new and full moons. Their imperial observatories equipped with bronze instruments of astonishing precision, charted lunar cycles not as myths, but as patterns woven into the fabric of the cosmos. Meanwhile, on the Indian subcontinent, navigators along the coasts of Gujarat and Bengal relied on lunar-timed tides to guide merchant fleets moving along routes that connected Africa, Arabia, and Southeast Asia. They understood, long before Western science could explain, that a new moon brought both the promise of easier port entry and the threat of treacherous waters. Yet, for millennia, even the brightest minds were left to speculate on why the moon commanded the sea. Aristotle believed the moon heated the water, swelling it like a pot warmed by fire, while other Greek authors proposed stranger theories. Some imagined that hidden winds slumbered beneath the ocean's surface, awakened by the moon's radiance. But though their guesses were wrong, their curiosity pushed forward a tradition of inquiry that would eventually stumble toward the truth. The Greek thinker Pytheas, who ventured into the Atlantic around 330 BCE, provided one of the earliest written suggestions that the tides followed the moon's motion, a realization he likely gained from observing the dramatic shifts along the coast of Brittany. His accounts, though doubted by contemporaries, left faint echoes that would shape future generations' understanding. Centuries passed, kingdoms rose and crumbled, and the ocean continued its vast, unbroken breathing. In Roman ports like Ostia, harbor masters kept close watch on tidal patterns to ensure that grain ships from Alexandria could safely enter. Far to the north, the Celtic tribes of Britain and Gaul built settlements along estuaries shaped by tides so powerful they sculpted entire landscapes. And in the rugged fjords of Scandinavia, where Norse sailors learned to read the sea with an instinct honed by survival, the moon became an essential guide. Their sagas speak of voyages timed with favorable waters, and though they're framed in myth, these narratives reflect an empirical familiarity with tides gained through daily life. When the Arab world entered its golden age of science, scholars in Baghdad, Basra, and Damascus analyzed Greek, Indian, and Persian texts, refining and expanding earlier observations. Al-Biruni, one of the most brilliant polymaths of the 11th century, wrote that the tides were directly related to the moon's position, an insight far ahead of much European thought at the time. His works, filled with precise measurements and geometric reasoning, built a foundation for an explanation still incomplete but inching closer to a true physical understanding. Meanwhile, in China's bustling port cities during the Song dynasty, engineers developed elaborate tidal prediction systems to assist naval operations and commercial shipping. Their astronomers recognized the lunar-solar nature of tides and created tables that tracked the interactions between lunar cycles and seasonal variations. Yet despite all this progress, a full comprehension of the underlying physical mechanism remained elusive. The idea that invisible forces could act across empty space was deeply unsettling to ancient thinkers, who generally believed contact was required for influence. Everything changed as Europe approached the scientific revolution.
With the invention of improved telescopes and increasingly accurate timekeeping devices, the relationship between celestial motion and terrestrial phenomena became clearer. Galileo, observing the moon's craters and the phases of Venus, laid groundwork that encouraged thinkers to seek mechanical explanations for natural processes. René Descartes proposed that tides were caused by swirling vortices of subtle matter. His theory was wrong, but it represented the era's growing willingness to challenge ancient assumptions. Then came Isaac Newton, whose monumental Principia Mathematica in 1687 presented a vision of the universe governed by universal gravitation. For the first time, gravity was proposed as a force that operated not through contact but across distance, binding the motions of planets, moons, and oceans alike. Newton explained that the moon's gravitational pull drew Earth's water toward it, creating bulges on the side facing the moon, and, through the interplay of inertia and gravitational gradients, on the side opposite as well. This elegant reasoning at last offered a framework that unified the celestial with the terrestrial. Still, Newton's work was only the beginning, for understanding the tides in their full complexity required far more than recognizing the pull of the moon. As the 18th century unfolded, mathematicians like Pierre-Simon Laplace constructed equations that considered Earth's rotation, the depth of ocean basins, and the constraints imposed by continental boundaries. These advances allowed scientists to predict tides with greater accuracy, turning what had once been the province of superstition into a cornerstone of navigation. In bustling maritime hubs, London, Amsterdam, Lisbon, and Boston, tidal almanacs became indispensable tools, consulted by captains whose fortunes depended on timing their arrivals and departures precisely. Every port came to possess its own tidal signature, shaped not only by lunar cycles, but by the unique geography of its coastline. During the age of exploration, tides influenced more than trade. They determined the outcomes of empires. When Ferdinand Magellan's crew drifted through the straits that would bear his name, they observed tidal currents so fierce they mistook them for the breath of some monstrous creature lurking beneath the waves. In the Indian Ocean, where monsoon winds partnered with lunar tides, fleets of merchant ships followed routes that changed with the seasons, forging global connections centuries before the term globalization existed. And on the coasts of the Americas, the Spanish conquistadors contended with tidal flats that stranded their vessels, shaping the pace and direction of their conquests. As industrialization transformed the 19th century, the study of tides became increasingly exact. Observatories from Hamburg to Bombay installed precision tide gauges, allowing researchers to track variations minute by minute. This data revealed subtle patterns, monthly oscillations tied to the moon's elliptical orbit, annual cycles influenced by the tilt of Earth's axis, and long-term shifts caused by the slow precession of lunar nodes. Engineers designing bridges, docks, and harbors needed to understand these patterns intimately, for mistaking a region's tidal range by even half a meter could doom an entire project. The science of tides, once rooted in myth and observation, had become a discipline blending astronomy, mathematics, hydrodynamics, and geology into a single, evolving symphony.
At the same time, far from the world of laboratories and academies, traditional coastal communities maintained their own knowledge systems. Fishermen in Brittany still listened to the whisper of tidal currents swirling through narrow channels carved by glaciers long vanished. Pearl divers in the Persian Gulf timed their expeditions with lunar cycles known to their ancestors. And on the shores of Japan, where tidal currents met the demands of a growing imperial power, pilots guided ships through treacherous waters using skills that bridged modern charts with centuries-old intuition. Thus, the moon's influence remained both a scientific reality and a cultural inheritance, shaping human behavior across eras and continents. In the late 19th century, as steamships replaced sails and telegraph wires stitched continents into an unprecedented network of communication, the precision of tidal prediction became an instrument of both science and statecraft. Navies required exact knowledge of shallow water passages where a misjudged tide could leave a warship helpless on a sandbank, and commercial fleets demanded accurate schedules that synchronized with the rhythms of the ocean as reliably as railway timetables synchronized with the turning of wheels. Across the British Empire, engineers built tidal prediction machines, intricate analog computers of brass gears and rotating pulleys designed to mimic the sinusoidal dance of lunar and solar cycles. These marvelous devices, weighing hundreds of kilograms and polished to a shine that reflected the pride of their makers, could forecast months of tidal data at the turn of a crank. Their dials traced elegant curves that allowed harbor masters from Singapore to Cape Town to plan shipping operations with newfound confidence. Each oscillation on the paper drum represented the pull of celestial bodies mediated through the mechanics of metal craftsmanship. In France, where the Atlantic coast experienced some of Europe's most dramatic tidal ranges, mathematicians worked to refine harmonic analysis, decomposing tides into dozens of constituent waves, each representing a specific astronomical influence or terrestrial interaction. This analytical approach revealed that the tide was not merely a simple rise and fall, but a complex superposition of motions layered atop one another. Some components followed the 12-hour lunar semi-diurnal cycle. Others adhered to the 24-hour solar diurnal rhythm, while others stemmed from the moon's elliptical orbit, its nodal precession, or seasonal variations tied to Earth's axial tilt. By unraveling these layers, scientists approached the tides the way a music theorist might dissect a symphony, identifying the contribution of each instrument within the sweeping orchestral whole.
At the turn of the 20th century, as global exploration mapped the last blank spaces on the world's coastlines, tides revealed landscapes previously hidden from human experience. Along the shores of northern Australia, vast tidal flats spread across distances so great they became temporary deserts twice each day, exposing shipwrecks, ancient footprints, and fossilized riverbeds. In the Canadian Bay of Fundy, the world's most extreme tides carved cliffs and caverns that transformed with every cycle, erasing one set of shapes only to sculpt another. Scientists studying these extremes realized that the ocean did not respond uniformly to the moon's pull. Instead, the energy of tidal motion resonated within basins, much like sound resonates in a cathedral, amplifying in some regions while muting in others. This insight introduced a new layer of complexity, showing that the Earth itself had its own acoustics, its own hydrodynamic temperament that interacted with celestial forces in ways both predictable and profoundly intricate. As the World War erupted, tides gained yet another dimension of significance. Military strategists recognized that landing operations depended heavily on tidal timing. At Gallipoli, commanders underestimated how quickly the sea withdrew, leaving troops exposed on beaches where they expected deeper cover. Later, during the D-Day invasion of Normandy, Allied planners devoted extraordinary attention to the timing of tides and lunar phases. They needed a low tide to expose the German fortifications and obstacles laid across the beaches, but not so low that landing craft would run aground far from their targets. A full moon was required to illuminate the airborne operations scheduled before dawn. These conditions aligned only a few days each month, and it was this narrow celestial window that determined the timing of one of the most consequential military actions in history. Thus, the moon, indifferent to human conflict, nonetheless played a silent role in shaping the fate of nations. In the decades following the war, oceanography emerged as a modern science powered by new technologies. Submarines probed deep currents, while research vessels anchored in remote seas recorded tidal patterns with atomic precision. Scientists discovered that tides extended far beyond the classical picture of rising and falling shorelines. In the deep ocean, vast tidal waves, called internal tides, propagated along layers of differing water density, unseen from the surface, yet crucial to the mixing of nutrients and heat throughout the marine environment. These internal tides, hundreds of meters tall, though nearly invisible to the naked eye, influenced migration patterns of marine life, shaped underwater ecosystems, and affected the distribution of temperatures that, in turn, impacted global climate. Their study revealed the tides as a three-dimensional phenomenon, not merely a surface effect, but a dynamic force sculpting the entire oceanic body. At the same time, the space age began to reshape humanity's understanding
of the gravitational interplay between Earth and Moon. When the Soviet Luna missions transmitted the first close-up photographs of the lunar surface, and when the Apollo astronauts later walked on its dusty plains, scientists gained direct insight into the Moon's mass, composition, and gravitational field. This data refined tidal theories further, revealing subtle variations in lunar gravity caused by mass concentrations buried beneath ancient impact basins. Although these anomalies exerted only faint influence on Earth's tides, their discovery underscored how complex the gravitational relationship between the two bodies truly was. With every new measurement, the Moon grew less a distant mythic presence and more a familiar companion whose influence could be quantified with astonishing precision.
Meanwhile, the development of satellites transformed tidal research in ways previous generations could scarcely have imagined. The launch of satellites equipped with radar altimeters allowed scientists to observe the height of the ocean's surface across the entire globe with centimeter-level accuracy. From this vantage point, patterns previously hidden in local observations emerged clearly. Planetary-scale tidal waves could be charted as they circled the oceans, revealing how continents redirected their flow, how deep trenches altered their speed, and how the Coriolis effect, born from Earth's rotation, twisted their paths into graceful spirals. Satellite data showed that the tides form a global tapestry of rotating systems called amphidromic points, locations where the tidal range is nearly zero and around which tidal crests rotate like the arms of a giant clock. These amphidromic systems, swirling in clockwise patterns in the southern hemisphere and counterclockwise in the northern, illustrated how the ocean's response to the Moon was not uniform, but sculpted by Earth's geometry, rotation, and bathymetry. In this same period, marine archaeology uncovered ancient structures built in harmony with the tides, revealing the long arc of human adaptation. On the coasts of the British Isles, researchers discovered Iron Age fish traps, combs of stone walls designed to capture fish as the tide receded. In the Mediterranean, remnants of Phoenician harbors showed careful engineering that accounted for tidal variations, even in regions where the tidal range was modest. Along the Pacific Northwest, indigenous communities constructed vast wooden weirs that exemplified a deep understanding of the tidal patterns governing their waters. These artifacts spoke not merely of survival, but of societies that lived in symbiosis with the Moon's pull, using it as a reliable rhythm to sustain thriving cultures long before written records. As the 21st century dawned, climate science added yet another dimension to the study of tides. Rising sea levels altered tidal dynamics, amplifying storm surges that rode atop the lunar-pulled waters. Cities built on tidal deltas, Jakarta, Dhaka, New Orleans, Venice,
faced increasing vulnerability as the boundary between land and sea shifted. Engineers analyzing these challenges realized that future coastal defenses would need to incorporate models that accounted for interactions between lunar cycles, changing ocean temperatures, melting ice sheets, and shifting weather patterns. Tidal science, once confined to predicting water heights for sailors, became a critical tool for understanding the resilience of entire civilizations. Yet the moon's influence extends not only into the realms of science and engineering, but into the subtler domains of biology. In coastal ecosystems, countless species have evolved life cycles synchronized with the tides. Horseshoe crabs crawl onto beaches during spring tides to lay eggs, providing a seasonal feast for migrating birds. Grunion fish in California leap ashore during specific lunar phases to spawn on the sand, their timing so precise that entire festivals have formed around witnessing these shimmering spectacles. Coral reefs in the Indian and Pacific Oceans release their gametes in mass spawning events triggered by the combined cues of temperature, daylight, and lunar illumination. These biological rhythms, woven into the gravitational cadence of the moon, illustrate how deeply the pulse of celestial mechanics permeates the living world.
Astronomers studying exoplanets have even speculated that moons may play a pivotal role in making planets habitable. Without the stabilizing influence of our moon, Earth's axial tilt might vary chaotically, leading to extreme climatic swings that could challenge the persistence of life. Moreover, tidal forces may have stirred Earth's early oceans, promoting the chemical mixing necessary for the emergence of life itself. The interplay between the moon and the ocean, therefore, is not merely a feature of Earth's present, but may have been essential to its beginning, a gentle celestial stirring that encouraged the first whispers of biology on a young and restless planet. Meanwhile, on the ocean floors, research revealed that tidal forces even influence tectonic activity. In regions where the crust is stretched thin, such as mid-ocean ridges, the slight daily flexing caused by tides can trigger subtle increases in volcanic activity and hydrothermal vent emissions. These deep-sea vents, teeming with life that thrives on chemical energy rather than sunlight, may also owe part of their dynamic cycling to the lunar pull. Thus, the moon's influence penetrates from the surface waves down to the darkest trenches, touching processes both biological and geological. The integration of supercomputers further revolutionized the field. With the power to simulate tidal flows across resolutions of meters rather than kilometers, scientists could model how water moved around islands, through straits, and across continental shelves, with extraordinary detail. These simulations revealed how tidal currents transported sediments that shaped coastlines, how energy dissipated at underwater sills that stirred nutrient-rich water upward, and how tides interacted with storm systems to produce surges that could devastate unprepared communities. Equipped with this knowledge, architects and planners began designing structures that worked with the tides rather than against them. Floating buildings, tidal energy turbines, and flexible breakwaters that absorbed the moon-driven motion instead of resisting it. In laboratories far from the sea, physicists used the tides to test the precision of gravitational theories. Instruments designed to measure the slight stretching and compression of the Earth's crust due to tidal forces helped refine models of Earth's elasticity. These experiments even contributed to the calibration of gravitational wave detectors, which required the ability to distinguish ripples in space-time from the much larger influence of lunar tides tugging gently at the ground beneath them. The moon, which once inspired myth, now served as a calibration tool for instruments listening to the distant echoes of colliding black holes.
As the reach of tidal research expanded, attention turned to regions where the moon's influence created phenomena so peculiar they challenged long-held assumptions about the predictability of ocean motion. Nowhere was this more evident than in the narrow estuaries of China's Qiantang River, where the world's largest tidal bore thundered upstream with a roar that could be heard kilometers inland. Locals called it the Silver Dragon, a name that captured both its shimmering form and its fierce serpentine power. Centuries-old records described how emperors, poets, and court astrologers traveled to the riverbanks each autumn to witness the boar's arrival, its timing governed by the alignment of the moon with the equinox sun. As modern hydrodynamicists studied this spectacle, they realized that tidal bores were not merely curiosities, but windows into nonlinear wave dynamics, where the moon's gentle gravitational pull, when funneled into narrowing channels, transformed into a towering wall of water, racing faster than a galloping horse. Observing such extremes allowed scientists to refine their understanding of how energy cascaded through tidal systems, revealing that even the most predictable celestial forces could unleash dramas of astonishing complexity. In South America, the Amazon River's pororoca presented a similar story, an immense surge of tidal energy racing inland along the world's broadest river mouth, carrying with it driftwood, silt, and sometimes entire trees. For centuries, indigenous communities had learned to anticipate the pororoca's arrival, adapting their fishing, travel, and settlement patterns to its commanding presence. Early explorers misinterpreted the phenomenon as a sudden storm-driven deluge, unaware that the moon's far-reaching pull had summoned this unstoppable crest from the Atlantic's edge.
As researchers mapped the pororoca's behavior using aerial photography and remote sensors, they discovered that the shape of the ocean floor far offshore, subtle changes in depth and slope, stretching across hundreds of kilometers, determined how the bore would form, how high it would rise, and how far it would travel. The tides, it became clear, were not local happenings, but sprawling expressions of the planet's interconnectedness, with causes and effects spanning distances that defied intuition. In Europe, the power of the moon left its mark not only on natural landscapes, but on human engineering achievements. The construction of vast tidal mills along the coasts of Brittany and Normandy in the Middle Ages demonstrated how early communities learned to harness the moon's pull for mechanical work. These mills, built in stone and timber, trapped seawater in reservoirs during high tide and released it through narrow channels to turn heavy wooden wheels. Their rhythmic operation followed the celestial schedule without need for human intervention. In some coastal towns, these mills operated for centuries, grinding grain for entire regions and offering a quiet testament to the regularity of the moon's influence. When modern engineers restored these structures for historical study, they found that the positioning of sluice gates, the angle of mill races, and even the shape of the reservoirs reflected a deep empirical understanding of tidal hydraulics, knowledge acquired not through mathematical theory, but through generations of careful observation.
The tides have also shaped artistic imagination in ways often overlooked by scientific narratives. Ancient Greek dramas set along coastal sanctuaries referenced the moon as a conductor of the waters, its phases woven into metaphors of fate and renewal. In medieval Japanese poetry, the tide's ebb and flow symbolized the impermanence of worldly concerns, mirroring the Buddhist notion of life's transient nature. European painters of the Romantic era, captivated by the sublime interplay between sea and sky, depicted coastlines at low tide with stranded boats leaning on their keels, visual cues signaling the unseen hand of the moon. Even when unspoken, the moon's pull lingered in these works as an implicit force shaping mood, setting, and symbol. As research vessels pushed into the polar regions, scientists encountered yet more evidence of tidal influence in unexpected contexts. In Antarctica, where massive ice shelves floated atop the frigid Southern Ocean, tidal forces lifted and lowered these frozen platforms by several meters each day. This flexing, though slow and subtle, created fractures deep within the ice, influencing calving events that reshaped coastlines of ice hundreds of meters thick. In the Arctic, where warming temperatures opened new shipping routes, tides interacted with sea ice to produce complex mosaics of leads, ridges, and pressure zones. Indigenous Arctic communities, whose survival depended on navigating this ever-shifting domain, developed intricate knowledge systems describing how tides affected ice stability. Their insights, passed orally through generations, enriched scientific models that otherwise struggled to account for the delicate interplay between lunar forces, temperature gradients, and wind-driven drift. In the Indian Ocean, marine biologists discovered that tidal cycles played a critical role in the behavior of plankton blooms. These microscopic organisms, forming the base of marine food webs, rose and fell through the water column in synchrony with tidal currents. The moon's pull effectively acted as a global stirring mechanism, influencing the availability of nutrients and oxygen throughout the region. By analyzing genetic material collected from drifting sensors, researchers found that certain plankton species synchronized their reproductive cycles with the spring tides, maximizing their chances of population expansion when currents dispersed them most widely. Thus, the gravitational rhythm traced by the moon etched itself into the evolutionary strategies of organisms too small to be seen with the naked eye.
Looking further into geologic time, scientists studying ancient sedimentary layers uncovered ripple marks preserved for hundreds of millions of years, fossilized testimonies of ancient tides. These patterns revealed that during the age of the dinosaurs, Earth's days were significantly shorter and its tides more frequent. By analyzing the thickness of sediment bands deposited in tidal flats, researchers reconstructed the gradual retreat of the moon as tidal friction transferred Earth's rotational energy outward. In rocks older still, dating back to the Precambrian era, faint tidal imprints suggested that the moon once orbited much closer, its gravitational pull generating tides of staggering scale that helped shape early coastlines in ways no longer possible today. Through these geologic archives, the story of the Earth-Moon system became a chronicle spanning billions of years, with the tides serving as both witness and participant in the planet's unfolding history. Advances in underwater monitoring technology brought additional revelations. Networks of seafloor sensors detected minute changes in pressure as tides passed overhead, allowing scientists to map abyssal plains and submarine canyons with extraordinary precision. In deep trenches like the Mariana and Tonga, tidal forces caused subtle changes in water density that influenced the behavior of creatures living at pressures so immense their bodies glowed with bioluminescent hues when disturbed. In volcanic island arcs, the pressure changes associated with tides modulated the release of gas from undersea vents, hinting at a delicate dialogue between Earth's solid interior and the liquid mantle of the oceans above. These discoveries led geophysicists to consider whether the moon's pull influenced seismic activity in regions of heightened tectonic stress. While the connection remained a subject of debate, data from certain fault zones suggested that tidal stresses could act as the final nudge triggering micro-earthquakes that otherwise lay poised on the brink of release. Meanwhile, The study of tidal energy opened new horizons in sustainable power generation. In Scotland's Pentland Firth, where the Atlantic Ocean squeezed between the mainland and the Orkney Islands, tidal currents reached speeds that rivaled river rapids. Engineers installed underwater turbines anchored to the seabed, their blades turning steadily in response to the moon-driven flow. These turbine arrays, designed to operate reliably for decades, required detailed knowledge of not only daily tidal cycles, but long-term variations dictated by lunar nodes and perigee-syzygy alignments. In Alaska's Cook Inlet, where some of the world's strongest tides surged through narrow channels bordered by mountains, similar efforts aimed to harness the predictable rhythm of lunar energy. The promise of tidal power, reliable, renewable, and inextricably tied to the gravitational mechanics of the Earth-Moon system, stood as a testament to how modern technology could partner with ancient natural forces.
As global networks of GPS satellites improved positional accuracy to centimeters, oceanographers used these systems to observe how coastal land rose and fell with Earth's solid tides, subtle deformations of the crust caused by the same gravitational pull that shaped the ocean's surface. These solid Earth tides, typically amounting to mere tens of centimeters, demonstrated that the moon's influence permeated even the rocky foundations beneath continents. By studying these deformations, scientists refined models of Earth's internal structure, revealing variations in mantle viscosity and crustal rigidity. Such insights proved crucial for understanding volcanic activity, plate tectonics, and the long-term evolution of Earth's shape. Researchers also turned their attention to the behavior of the atmosphere under lunar influence. Though far less pronounced than ocean tides, lunar atmospheric tides created slight variations in air pressure, driven not only by solar heating, but by the moon's gravity. These lunar atmospheric tides, detectable through sensitive barometric measurements, influenced wind patterns at high altitudes, subtly modulating the jet streams that guided weather systems across continents. Understanding these effects helped meteorologists improve models of long-term climate behavior and refine predictions of seasonal anomalies. The moon's influence manifested even in human culture at scales both grand and intimate. Coastal festivals timed with spring tides blended scientific accuracy with traditional celebration. In Southeast Asia, communities gathered to observe the sea receding far beyond its usual boundary, revealing sandbanks that served as temporary walkways between islands. In Northern Europe, entire towns hosted nighttime low-tide walks across seabeds normally hidden beneath meters of water, turning the lunar cycle into a shared ritual that connected modern citizens with their ancestors. In the South Pacific, where entire island chains rose like stepping stones across the ocean's vast expanse, traditional navigators retained an understanding of tides so refined it rivaled the precision of modern charts. Among the Polynesian masters of wayfinding, knowledge of how swells wrapped around atolls, how tidal currents bent between reefs, and how the moon shifted these patterns from night to night formed an intimate part of their navigational art. These seafarers read the sea by touch as much as by sight, feeling through the hull of their canoes the faint tug of lunar-driven currents hundreds of meters wide. Oral histories, preserved through chants and genealogical recitations, described the seasonal alignment of stars with the strength of particular tidal flows, embedding scientific observations within cultural memory in ways that allowed this knowledge to survive for millennia without a single written word. Their voyages, stretching across thousands of kilometers, became living proof of how deeply and instinctively humanity could understand the moon's influence when necessity sharpened observation and experience shaped interpretation.
As anthropologists studied these traditions, they realized that tidal knowledge in Polynesia, Micronesia, and Melanesia was not confined to navigation alone. It guided the placement of fish traps, the rotation of communal agricultural cycles near coastal plains, and even the scheduling of regional gatherings that depended on predictable weather and safe water passage. Lunar calendars intricately interwove the visibility of stars, the position of the moon, and the seasonal behavior of the tides into systems of governance and spiritual practice. These calendars often differed from one island group to another, each tailored to the subtle tidal signatures unique to its surrounding waters. Through these systems, communities forged a relationship with the moon that extended beyond simple economic or geographic necessity. It became a cultural constant, as embedded in their identity as the carved wood of their temples or the woven patterns of their mats. Meanwhile, in Africa's coastal regions, the tides shaped human settlement in equally profound ways. Along the eastern shores bordering the Indian Ocean, Swahili trading cities flourished in tidal environments that offered harbors sheltered from monsoon storms. Archaeological excavations in places like Kilwa Kiswani and Mombasa revealed ancient docks whose foundations showed clear adaptation to the rhythmic rise and fall of the sea. Stone stairways descending into the water bore grooves worn by centuries of mooring ropes that tightened and slackened with the moon's pull. The timing of maritime trade, which connected East Africa to Arabia, Persia, India, and beyond, depended not only on wind, but on the tides that determined when heavily laden dhows could safely enter shallow harbors. The prosperity of these city-states, with their elegant coral stone architecture and bustling markets, owed much to the silent guidance of lunar forces that shaped the rhythm of coastal commerce. Further south, along the vast sweep of the Namib Desert, the interaction between ocean tides and desert winds produced landscapes found nowhere else on Earth. In regions where the desert's towering dunes descended directly into the sea, tidal action sculpted lagoons that teemed with life against the stark backdrop of sand. Flocks of flamingos gathered in shallow waters exposed by low tide,
feeding on algae stirred by the moon's pull, while early European explorers marveled at how such richness could exist in an environment so seemingly inhospitable. Scientists studying these ecosystems found that the nutrient cycles sustaining them hinged upon the predictable exchange of water driven by the tides, which replenished lagoons, flushed stagnant zones, and enabled microhabitats to thrive. Even in a desert that had remained largely unchanged for millions of years, the moon's influence carved out pockets of abundance where life flourished against all odds.
Across the globe, indigenous knowledge systems carried their own traditions of tidal understanding. On the western coast of South America, the Mapuche people of Chile developed fishing methods that seamlessly integrated local tidal rhythms. Their wooden rafts, constructed from lashed reeds, were designed to navigate the tidal flows of estuaries, where currents shifted direction twice daily with remarkable precision. Oral stories told of ancestral figures who guided communities by predicting the tides based not on lunar calendars alone, but on the interaction of lunar phases with seasonal winds, an empirical understanding encoded in mythic form. In the North Atlantic, Inuit communities along the coast of Greenland and Canada relied on careful observation to avoid the dangers posed by tidal cracks forming in sea ice. These cracks, invisible beneath fresh snow, yet capable of swallowing sleds and hunters alike, opened and closed with the moon's invisible tug, turning the frozen landscape into a shifting mosaic where survival depended on recognizing subtle signs in the ice's texture and sound. While traditional knowledge illuminated the local consequences of tidal motion, scientific inquiry continued to unravel the deeper mechanisms by which the moon governed these vast forces. In laboratories studying fluid dynamics, researchers experimented with rotating tanks filled with dyed water, simulating the effect of Earth's rotation on tidal waves. By adjusting the speed of rotation, the shape of the basin, and the frequency of oscillation, these experiments recreated the amphidromic systems observed in the real ocean. The swirling patterns that emerged, spiraling crests around nodes of stillness, provided tangible insights into behaviors that defied simple explanation. These visualizations showed how the moon's gravity, acting uniformly across the globe, could produce intricate patterns once filtered through the irregular geometry of continents, the varying depths of basins, and the turning of the planet beneath the moving water. This understanding grew even more sophisticated with the advent of numerical modeling. Supercomputers running complex simulations revealed that the tides dissipated enormous amounts of energy, roughly 3 terawatts, through friction between the moving water and the ocean floor. This energy loss exerted a braking effect on Earth's rotation, causing days to lengthen by fractions of a millisecond each century.
Over geological timescales, this deceleration accumulated, transforming the length of a day from the swift 6-hour rotation Earth experienced billions of years ago to the 24-hour period familiar today. Meanwhile, as angular momentum transferred from Earth to the Moon gradually receded, its orbital radius increasing by about 3.8 centimeters each year. This outward drift, verified through laser ranging experiments conducted using reflectors left by Apollo astronauts, provided a direct measurement of the tidal interaction shaping the long-term evolution of the Earth-Moon system. In the context of planetary science, these insights proved invaluable. By comparing Earth's tides to those predicted on other worlds, astronomers gained clues about the internal composition of distant moons and planets. For instance, the intense tidal flexing of Jupiter's moon Io, driven by gravitational interactions with Jupiter and neighboring moons, generated volcanic activity unparalleled anywhere else in the solar system. On Saturn's moon Enceladus, tidal heating beneath the icy crust maintained a subsurface ocean that erupted through geysers detected by spacecraft, raising tantalizing possibilities about extraterrestrial habitability. In these cases, the same gravitational principles that lifted Earth's tides played out on worlds vastly different from our own, demonstrating that tidal forces were not a mere terrestrial curiosity, but a universal phenomenon shaping planets, moons, and perhaps even the prospects for life in distant star systems. Yet while these distant examples expanded the scope of tidal science, the most pressing concerns remained closer to home. Coastal cities around the world began confronting the growing challenge of sunny day flooding, in which high tides, particularly during Perigean spring tides, when the moon approached closest to Earth, pushed seawater into streets, parks, and basements, even in the absence of storms. These events, once rare and remarkable, became increasingly frequent as sea levels rose. Urban planners, faced with the encroaching reach of the tides, consulted tide records spanning centuries to project the future boundaries between land and sea. Tide gauges installed during the colonial era in ports such as Mumbai, Sydney, and San Francisco provided invaluable long-term data showing how the interplay between lunar cycles and global ocean dynamics shaped the shifting coastlines. In this emerging reality, understanding the tides became essential not only for scientists, but for policymakers, architects, and emergency managers. The construction of seawalls, storm surge barriers, and elevated infrastructure demanded precise calculations that accounted for the full spectrum of tidal influences, from the twice-daily cycles to the fortnightly spring neap rhythm, the monthly perigee-apogee variation, and the long-term lunar nodal cycle repeating every 18.6 years. Each layer contributed to the ultimate height reached by water during extreme events. Engineers recognized that neglecting even one component could lead to catastrophic underestimation of risks. The moon, once a poetic symbol in the night sky, asserted itself as a vital factor in the planning of cities whose futures depended on understanding its influence down to the centimeter.
Yet, despite these challenges, the tides also offered new opportunities. Research into tidal ecosystems revealed that salt marshes, mangrove forests, and seagrass meadows, habitats shaped daily by the moon's pull, provided powerful natural defenses against coastal erosion. These ecosystems trapped sediments carried by the tides, built land upward over time, and dissipated wave energy before it reached the shore. Conservationists, working with hydrologists and ecologists, began restoring these environments not only to protect biodiversity, but to harness their natural resilience in the face of rising seas. In doing so, they rediscovered what ancient communities had long understood: that living with the tides, rather than resisting them, often offered the most enduring solutions. In the deep ocean, another form of tidal interaction captured scientific attention: the mixing of heat between layers of water. Tidal forces interacting with undersea mountains generated turbulence that transported warm surface water downward and cold deeper water upward. This vertical mixing played a crucial role in regulating Earth's climate by influencing how heat moved through the ocean, which in turn controlled the pace of atmospheric temperature change. Climate models incorporating detailed tidal mixing processes produced more accurate forecasts, demonstrating that the moon's influence extended far beyond the coastal realm and into the global energy balance that governed Earth's long-term stability. Even the study of marine acoustics found relevance in tidal science. Sound waves propagated differently depending on the density, temperature, and movement of water, all of which varied with tidal cycles. Naval operations relying on sonar needed to account for these variations to avoid misinterpreting echoes distorted by shifting layers of water. Marine biologists tracking whale migrations discovered that certain species timed their deep dives to coincide with slack tide, the brief period when currents reversed direction, because the reduced noise and turbulence allowed them to communicate across greater distances. In this way, the moon's pull shaped not only the motion of water, but the movement and behavior of creatures inhabiting its depths.